over P2 exponents and radicals. So integer exponents. In property 3 below, be sure you see how to use a negative exponent. So the property of exponents, you let a and b be real numbers, variables, or algebraic expressions, and you let m and n be integers. All denominations are based on non-zero numbers. So if you look at property 1, we'll go one property at a time. Notice how we have the same base. So we have a to the n power, a to the n power. So it's going to be adding a m plus n as the exponents because the base is the same. That is the key part for it to work. If it's not the same base, you cannot add the exponents. Same thing applies for number 2. We have a to the n power over a to the n power, which just ends up being a subtraction. Because we have the same base, we can just say it's a and then m minus n as the exponents. If you look at example 1 and example 2, for example 1, our base is a number, so we have 3 squared times 3 to the 4th. We end up adding them to become 3 to the 6th power, which ends up being 729. Now for 2, we have a division, so we end up subtracting the 7 and the 4, which they come from the same base of x. So we get x to the 3rd power. Now for number 3, we have a negative exponent. We have a to the negative n. So remember, if it's a negative exponent, it doesn't mean it's wrong. It just means it's in the wrong place. All of the numbers have a denominator of 1, which in this case we have to apply, and we got to flip the fraction. Look for the inverse. So it would be 1 over a to the n power. Now, right here, we have this, which honestly, I will never ask you to put it in that format. Please leave your work in the first equal, the 1 over a to the n power. Because if it happens that the numerator is not 1, then it will not equal the same thing. So for the example, we have y to the negative 4th, it becomes 1 over y to the negative 4th. If we were to put it into this form, the only reason it's correct is because 1 to the any power is going to be 1, and y to the 4th power is still y to the 4th. If you happen to have a different numerator, because for some reason you have a number in front of it, let's say 2, you can't do this because that would be 2 to the 4th power, like I wrote on the board. So it would be wrong. So please just try, be consistent. If you leave them like this, that is completely okay. I don't need you guys to put it in parentheses. I don't want you guys getting it wrong because you took an extra step. It is simplified though when it is positive. So if you have a negative exponent, you're not done. Again, but you don't have to put it into the parentheses. For number 4, we have a to the 0 power. The rule is if anything to the 0 power, as long as the base is not 0, it will be equal to 1. So if you notice, we have x squared plus 1 as the example to the 0 power equals to 1. Anything to the 0 power is equal to 1. Doesn't matter what it is. 5, we have ab to the power m. We're going to be able to distribute that exponent into both a and b. As it shows right here, we have a to the n power, b to the n power. And in the example, we have that 3 that gets distributed into the 5 and into the x. So we get 5 to the 3rd power, x to the 3rd power. Then you simplify by doing 125x cubed. Again, you simplify because the 5 can be simplified by multiplying it by itself 3 times and or cubing it, in other words. For 6, it's the exact same thing. The only difference is now we have an exponent inside of the parentheses. All we end up doing at the end is multiplying the same way we did before. We multiply that n into the a to the n power, end up just multiplying a equals m times n. In the example, we have y to the 3rd power times negative 4 when it's raised. So we get y to the negative 12. Notice how they simplified it at the end as 1 over y to the 12th power. That will be the answer I would like you guys to leave it at. This is ideal how the simplification goes. Again, the parentheses can cause trouble at the very end. For number 7, we have a over b to the n power. Because we're raising a power to the equation, we're going to distribute that power into all the terms. So we end up with a over m over b over m. Now we do not simplify it because they are not the same base, so we cannot subtract like we do in number 2. The key there is the same base. In the example for 7, we have 2 over x, all of that to the third power, so we end up with 2 cubed over x cubed, which is just 8 over x cubed. Again, because it's different bases, we do not simplify. Or, well, that is as simplified as you can get it. And for number 8, if you have an even exponent, as long as it's inside the parentheses or inside the absolute value, the answer will be positive, no matter what. The only way you will get a negative answer if you have an exponent is it's written outside, kind of like this, like it did on the board right there. This negative is not part of the squaring. But if it's inside the parentheses, may that be like this, may that be as an absolute value on the outside or on the inside, those will all give you positive values. Now, for example 3, they're asking you to use properties of exponents. So use the properties of exponents to simplify each expression. So I'll do A with you. I'll give you guys a couple seconds or a couple minutes to do B, C, and D. So to start off, for A, we have negative 3ab to the 4th power times 4ab to the negative 3rd power. I can actually go ahead and multiply like terms. So I can do the negative 3 with the 4, the A with the A, and the B with the B. I'm going to actually be following example 1. So when I do that, I end up multiplying the negative 3 times the 4. The A, because it's the same base, so I'll have an exponent of 1, so I end up with 1 plus 1. And then for B, I end up with 4 plus negative 3. So when I simplify that, I end up with negative 12a squared, b to the 1st power, or just b. For B, I'm going to actually be using the properties 5 and 6 because I am distributing that exponent into all of these terms. So I end up with 2 to the 3rd power, x to the 3rd power, and y to the 2nd times the 3rd power. So I end up with 8x cubed, y to the 6th power. Now see something interesting. That is actually the property number 4 that we went over in the last slide. Notice how the negative 4a squared is all to the power of 0. So I can actually just cancel that out, and I end up with 3a times 1. So it's just 3a as the final answer. And then for D, we're using the same property. We're going to distribute into all of the terms. So we end up with y squared, x3 to the times 2, and y to the 2nd power. That's going to simplify to 25, x to the 6, y squared as our final answer. Now we're going to go over radicals and their properties. So here are some generalizations about the nth root of the real number. The nth being the index. The index is that root right in front of the square root mark. That is the name. Its name is the index. So when they're saying that when a is greater than 0, n is even. So that's just a generalization. You also have a is greater than or a is less than 0, which is saying that n would be odd. We also have a is less than 0, so n is even. And then we have a is equal to 0, so n is even or odd. So what does this mean? Honestly, this is just a generalization of square root, 4th root, 5th root, 6th root, or cube to the 5th power. Alright, so this is just a generalization like I was saying. It's not always true. Sometimes you will have positive numbers with odd integers, or odd ends or indexes, and backwards. Now, the only one that's always a rule is the last one, which is when a is equal to 0. Doesn't matter if the index is either even or odd, because the answer is always going to be 0. Now you can have odd indexes, like we have in example 2, and end up with a negative number. if you have a negative number inside of the square root, like which is the base, and you have an even index, then that will also always be it's not a real number, so it's not a root. You will go and find I starting from there. Now, if you have an even root, the index, if you have an even index, you will have a positive root. Again, if you don't have a positive root, it's not a real solution, like it is stated in number 3. Now, for the integers 1, 4, 9, 16, 25, and 36, there's more than that. Those are perfect squares. They're perfect squares because we multiply a number by itself and get an even number. There are also cube roots 1, 8, 27, 64, 125. Again, there are more, which I'll call perfect cubes, because we have integers multiplied by itself 3 times to get that cube. Now I'm going to go over the property rules. So properties of radicals, so let a and b be real numbers, variables, or algebraic expressions such that the indicated roots are real numbers. And you let m and n be positive integers. So what does that mean? Notice how for number 1 we have n and then the square root of a to the m power. It says you can also write it as the whatever root n is and then raised to the m power. So giving you the example, it's written as the cube root of 8 squared equals, you can also write it as the square root of the cube root of 8. Now, whether you solve it by squaring 8 first, like it would be here, I'm writing this on the board. You can do 64 and take the cube root of 64, which honestly I think that would take a lot longer. Or you can just take the cube root of 8, which we know is 2, and then just do 2 times 2 would be equal to 4. At the end of the day, you will get the same answer. You choose the path that you prefer. Just make sure you show your work while you do it. Now for number 2, we have nth root of a times nth root of b. Because we have the same index, we can actually go ahead and multiply a and b. Like if we have, for example, we have root 5 times root 7, we get root 5 times 7, so we end up with root 35. We can't simplify root 35, as that is the simplest form already, but because we have the same index, we can go ahead and multiply them. Now for 3, we have the nth root of a over the nth root of b. You can actually write it outside. Notice how they wrote the nth square root of a over b, as long as b is not 0. In the example, that makes it easier, as you can simplify 27 divided by 9 into 3, so you get the 4th root of 3. For number 4, we have the root of m, and then inside we have the root of n of a. So you can also write it as multiply the indexes and the square root of a. The reason you can do that is because, remember, you can write all of these expressions as a fraction. So if I were to write this whole thing, I can write a 1 over n, and then because the root of m is for everything else, I can just do 1 over m. Following the rules of exponents, which you saw a few slides back, we can actually multiply those into a 1 over n m, which is just a different way of writing this part right here. So as you can see, we have 3, the cube root of the square root of 10. Remember, this square root of 10 is a 2. So we can actually just go ahead and do 3 times 2 to get the 6th root of 10. When you have stuff like number 5, when you have the index and the exponent exactly the same, you can cancel them out and you're just left with the base. And then for n, if it's an even number, then you're going to get the absolute value. Again, the n's cancel out from the same property as we used before. And if n is odd, you will end up with the negative, assuming the base is negative. Now, in the next slide, if you look at the small TV, notice we have example 9. It says using properties of radicals and use the properties of radicals to simplify each expression. Now, I'll go ahead and do a with you. For me to try to simplify this expression, I have to simplify the root 8 for me to be able to just multiply them together. So I can go ahead and factor it out with prime numbers. I prefer to factor with prime numbers because sometimes you're asked to take cube roots, 4th roots, 5th roots, and when I take them out with perfect squares, it takes a little bit longer. So I prefer to simplify by prime numbers. So if I do that root 8, I can do, well, 2 and 4, 2 and 2. Now, because the actual square root is just 2 of the same, I can take out a pair, and I'm left with 2 root 2 times root 2. Because now I have the exact same root, I can go ahead and multiply them. So I'm going to get 2 root 4. Now, again, root 4 is a perfect square, so I'm left with 2 times 2. So my final answer for this problem is actually 4. For B, C, and D, I actually end up using the property number 5 for all of these. If you notice B, I have the cube root, and it's raised to the third power, so I can actually just go ahead and cancel them out. And my answer is just the base, which is just 5. For C, I do the exact same thing. I can cancel out the index, which is 3, and the exponent, which is 3, so I'm left with just x. And for D, again, the exact same thing. I can simplify it by canceling out the index of 6 and the exponent of 6, which gives me y. So for this one, again, I'm going to just use the factor tree. It's my preferred method. If you do it differently, that's fine, as long as you show me the work. So I have it separated into 2 and 12, 2 and 6, 2 and 3. Now, because the index is 3, I look for 3 of the same kind. In this case, I have those 2's. So my final answer for this problem is going to actually be 2, and then the cube root of 3. So B is the 4th root of 48. Now I'm going to just start by factor tree. So I'm going to get 2 and 24, 2 and 12, 2 and 6, and 2 and 3. Because, again, in this case, the index is 4, I want to make sure I have 4 of the same kind. In this case, again, is 2. So my answer is going to be 2, and then the 4th root of 3, because that is the number that's left over here. So for C, I'm just going to go ahead and factor the 7, 5. So I'm going to separate it into 5 and 15, 5 and 3. So I can go ahead and, because it's a normal square root, I just take out the pair. So it's going to be 5 root 3x cubed. Now, but the x also can be simplified. If you notice, we have 3 x's and we only need 2 of the same. If I want to factor it out or just expand it, since we know the index is 2, we just want 2 of the same. So I can go ahead and take that out into the outside of the square root to getting 5x square root of 3x. Again, this x is the leftover, so it goes in there. But this is your final answer for this question. Now, for D, we're looking for the cube root of 24a to the 4th power. So I can go ahead and I'm going to start with 2 again. 2 and 12, 2 and 6, 2 and 3. Again, because the index is 3, I want 3 of the same. So take out that 2. So it's going to be 2, and then the cube root of 3a to the 4th. I can simplify that a to the 4th. If I were to expand it, I have 4 a's, but I only need 3. So I can take these 3 into 1 and take it outside of the square root. It's going to become 2a. It's going to be the cube root of 3a. Again, this is the remaining a that goes inside the root, and the remainder 3 that goes inside of the root. So for this problem, it's actually one of the easiest, I believe, because they just cancel out the index and the exponent, and you're just left with the base, which is 5x. That will be your final answer. If you forget that you can't do that, by all means, expand the problem. And notice that since we have 4 and the index is 4, you can just take one out and get the final answer, which ends up being the same 5x. So for example, in 11, they want us to combine the radicals. Now, I'm going to zoom in into A. In order to combine these radicals, since I'm not multiplying them, I have to get the under the square root part the exact same. So I'm going to actually factor the 48 and the 27 to simplify this radical before I can combine it. So 48, I'm going to separate into 2 and 12. Sorry, not 2 and 12. 2 and 24, then there's 2 and 12, 2 and 6, 2 and 3. Now, because it is a square root, I can take out 2 pairs, so I'm going to be on the outside 2, and then this is this 2. 2 times 2, because I have 2 pairs of the same, square root of 3, and then I'm going to have minus, and I'm going to do the exact same thing for the 27. So for the 27, I'm going to go ahead and factor it into 3 and 9, 3 and 3. Again, the pair that is there is at 3, so I bring down the original 3, and then times 3 root 3. I'm going to combine the 2 times 2 that I have outside on the other root. You could have done it at the beginning. I'm just doing it now to kind of go linear. So I'm going to have 2 times 4 root 3 minus 3 root 3. Now I can go ahead and multiply them since they are simplified as much as I can. So I'm going to multiply the 2 and the 4 to get 8 root 3 minus, and then the 3 times the 3 is 9 root 3. Because we have just 2 terms and they have the same square root, I can actually go ahead and combine them. So it's going to become 8 minus 9 and then root 3. So it's going to be negative root 3 as your final answer. Now to solve for B, I'm going to do the same thing. In order for me to be able to simplify this, I have to make sure these are the same inside of the square root once I simplify this radical. So we know 16 is a perfect root, but we're not looking for a perfect root, we're looking for a cube root. So it is important that you guys look at the index before you start. Now because this is a cube root, should change that to pen. So it's going to be 2 and 8, 2 and 4, 2 and 2. Wow. There it is. Now when I do that, since it's a cube root, we need 3 of the same kind. So I go ahead and take out those 3 2s. So it's going to be 2 and then the cube root of 2x. There's something I can do to that x to simplify it, so I'm going to leave it alone. Minus, let's find the cube root of 54. I'm going to start with 2. I just prefer to do it by prime numbers. If you do it differently, that's fine. So it's going to be 2, 27, 3 and 9, 3 and 3. Now when I do that, notice how they didn't come out in the same order as we usually do. But we have 3 of the same kind, which is a 3. So I can go ahead and take that and write 3. And then the cube root of 2x to the 4th. Remember, you can also factor out that x to the 4th. We need 3 x's in order to take it out. And we have 4. If it were to expand it, we have these 3. So I can go ahead and write this as 2, the cube root of 2x minus 3x, and then the cube root of 2x. Again, they match. They have the same index. They have the same radical underneath it. So I can go ahead and combine them. You can write them as 2 minus 3x and then the cube root of 2x. Now, since there's nothing I can do with the 2 minus 3x, now since you can't really combine the 2 and the negative 3x, you actually you're okay with writing it like this, or you can leave it like this. Either way is fine, as you can't really solve anything anymore. So rationalizing denominators and numerators. To rationalize the denominator or numerator of the form a minus b root m or a plus b root m, you multiply both numerator and denominator by its conjugate. So if you have an a plus b root m, you're going to multiply it by a minus b root m. Those are conjugates of each other. The reason they're conjugates of each other is because one is positive and one is negative. If the a is 0, then the rationalization factor of the root m is itself. For cube roots, choose a rationalization factor that generates a perfect cube. So if you have something like the cube root of 8, actually that's perfect. You have the cube root of 4, you want to multiply by the cube root of 2 to get the cube root of 8, which rationalizes to a 2. So in that case, we'll do some problems with it. Just keep in mind, if it's a normal square root, just multiply it by itself, because you need a pair. So when you multiply by itself, you make two of them. If you have a cube, try to make a perfect cube, like 1, 8, 27. I don't remember the other ones, but they're up there. So, for example 12, rationalizing single terms denominators. So, rationalize the denominator of each expression. In this case, we'll work this one together. The term that we had before was either a plus or minus b root m, if I'm not mistaken. It's going to be plus or minus because it is either one or the other. In this case, we have no a because we have nothing in front of that root. So because we have nothing in front of that root, I'm just going to go ahead and multiply the numerator and the denominator by the whole root. So in this case, it's going to be 2 root 3 on the top and 2 root 3 at the bottom. And you multiply across like you normally would. So the top is going to become 10 root 3 because we multiply the integers with the integers, and the root just kind of stays by itself. Now the bottom you're going to multiply the integers with the integers and the roots with the roots. What does that mean? When you multiply 2 times 2, you're going to get 4. But when you multiply root 3 times root 3, you're actually just going to end up with 3. So it's going to be 10 root 3, 4 times 3. So I'm going to go ahead and keep going up here. It's going to be 10 root 3 over 12. And you can simplify that. You can simplify the 10 and the 12. I'm going to divide by 2, so this becomes 5. And this becomes 6. So we end up with 5 root 3 over 6. That would be your final answer. The key part of rationalizing the terms is because you don't want a root on the denominator. So for 2 over the cube root of 5, like we said, we want to make sure this is a perfect cube root. Now, 5 is already a prime number and a small one at that. So in order for me to be able to get this to be a perfect cube root, I'm going to actually have to multiply by the cube root of 5 2 times. Now, why am I doing it 2 times? Because since it's a cube, we need 3 of the same. So this would make it 1, 2, 3, which will make it a perfect cube root. Now, when I do that, I multiply the top like I usually would. It's going to become 2, and then the cube root of 5 times the cube root of 5. You're going to multiply the cube roots together, so that's going to actually become 2 the cube root of 25. And then for the bottom, since we have the cube root of 5 times the cube root of 5 times the cube root of 5, because there are 3 of the same and it's the cube root, you're just going to get 5 at the very end. Because if you notice, we can write it as the cube root of 5 cubed. And following that same expression from a few slides ago, we can cancel these out, and that's why we end up with 5. So your final answer would actually be 2, the cube root of 25 over 5. Here they want to rationalize the numerator. So usually this will be perfect. This will be the answer you want. They're asking us to rationalize the numerator, so that means they don't want any roots up there. So we're going to do the same thing we would do as if it were the denominator. Now here we do have an a, so we're going to multiply it by its conjugate. The conjugate would be root 5 plus root 7 on the top, and root 5 plus root 7 at the bottom. You're going to FOIL the top. Remember, this is one term. And you're going to distribute the bottom. So I'm going to FOIL like this. And then I'm going to distribute for both of these. So it's going to be root 5 times root 5. I'll write down all the steps first. Root 5 times root 5. And then plus root 5 times root 7 minus root 5 times root 7 minus root 7 times root 7. And then at the bottom, it's going to be 2 root 5 plus 2 root 7. Now, following the same rules, root 5 times root 5 is just 5. So I'm going to go ahead and write that down. Root 5 times root 7 is root 35. And root 5 times root 7 is root 35. Since they are exactly the same and one's positive and one's negative, they end up canceling out. And then we're left with root 7 times root 7. That's going to be 7. So it's 5 minus 7. Then at the bottom is 2 root 5 plus 2 root 7. That's going to equal negative 2 root 5 plus 2 root 7. There's actually one more step I can do to simplify this. Since I have 2's on the top and on the bottom of every single term, I can actually simplify all of these and make them into 1's by dividing everything by 2. So I would end up with negative 1 over root 5 plus root 7. And that will be your final answer for rationalizing the numerator.
What if we left it at the 2?
If it were denominator with its conjugate, you would do the exact same thing, and it will cancel out for the denominator. So rational exponents. So definition of rational exponents. If a is a real number and n is a positive integer such that the principal nth root of exists, then a 1 over nth is defined as. This is kind of what I was talking about, that you can write the square roots into a fraction exponent. So a 1 over n, it's the same thing as saying the nth root of a, where 1 over n is a rational exponent of a. More so if m is a positive integer that has no common factor with n, then you can actually separate them into a square and root with exponents. Now I've talked about this throughout the lesson, giving you guys examples when we switch them. If you have the square root of x, you can write it as x at a half, because the square root is also always based on 2's. If you have the cube root, of x, it would also be x to the 1/3. Keep in mind, whenever there is a root radical, the exponent is always a fraction, and that number always goes on the bottom of that fraction. If you for some reason had the cube root of x, all of that raised to the 4th power, this would be 4 over 3, because the power goes on the numerator of that fraction and the root goes into the denominator of that fraction. So the rational exponents, the numerator of a rational exponent denotes the power to which the base is raised, and the denominator denotes the index of the root to be taken. That's what I was saying, that the index always goes at the bottom of that fraction and the power goes on the top. Now this is a different way of writing it with m, n, and b's. I wrote it with x and number examples, but it's the exact same idea. Here we have rational exponents. When you are working with rational exponents, the properties of integer exponents still apply. So for instance, you have 2.5 to 2 1/3. You can add the exponents, and then you will be left with 2 5 over 6. So if you for some reason cannot rationalize them, you can always write them into a exponent with a fraction and simplify the expression that way. That's also another way of simplifying if you are not able to simplify the radical. All right, so for example A, we have negative 32 to the power of negative 4 over 5. Remember, the fact that it's negative doesn't mean it's wrong, it's just not happy where it's at. So it's going to become 1 over negative 32, 4 over 5. Now that we have it in the place where it wants to be, we can start by doing this. I'm going to rewrite it into a radical form so you guys get a little bit more comfortable with what I'm writing. So it's the 5th root of negative 32nd to the 4th power. You could have also written it as 1 over the 5th root of negative 32nd and the 4th power on the outside. It really does not matter which one you prefer. Now, I think I'm going to take the 5th root first instead of multiplying 32 by itself 4 times, because that sounds like a pain. I'd really rather not do it. So when I do 32, I'm going to use the left one. I'm going to simplify into 2. And I'm just going to keep moving the negative down to see how many negatives I need. So it's going to be 2 and negative 16, 2 and negative 8, 2 and negative 4, 2 and negative 2. Now, when I do that, notice how I still have a negative outside in the 5 pairs, or, well, not 5 pairs, the pairs of 2. In the 5 numbers. So I'm going to take out a negative because even though it's the same number, keep in mind the radical is a negative. So it's going to become 1 over negative 2 to the 4th power. Now 2 to the 4th power is a lot simpler than negative 32 to the 4th power. So it's just negative 2 times negative 2 times negative 2 times negative 2. So it's 4 times 4. So we end up with 1 over 16 as our final answer. This is what I meant by try to go the easiest way that you possibly can. I could have done 32 times 32 times 32 times 32 and then taken the 5th root, and we still would have ended up with 16. But I just think it's easier to, when the numbers are that big, I think it's easier just to take out the root before you multiply the exponent or the power. So following the previous slide, notice that the bases are exactly the same. So because they are the same, I can just multiply the negative 5 times the 3 and combine the x's, since those exponents belong to that x. It's going to become negative 5 times 3, and then it's x, and at the top is going to be 5 over 3 plus negative 3 over 4, so it's just going to be, I'm going to write it the way I said it first, just going to end up being a subtraction at the very end. So we're going to be left with negative 15 x 5 over 3 minus 3 over 4. I'm going to find the common denominator, which is 12, so it's going to be negative 15 x, so 20 over 12 minus 9 over 4, and that's going to give me negative 15x, 11, oh wait, no, it's not 4, it's 12. 1 over 12, so it's going to be 11 over 12. That will be fine. This will be your final answer. You can leave it like this. So for C, they want you to simplify the rational exponent. We have the 9th root of a cube. So what I'm going to do is I'm going to write it okay, I guess this is weird. I'm going to write it as a 3 over 9, and that's going to simplify into a 1 over 3. I just simplify that exponent into a third, and this would be your final answer. If you want to rewrite it as the cube root of a, you can, but you can also know that you can leave it as a fraction, as in the a with the exponent as a fraction, and that's fine. Now for the second one, D, remember that you can multiply the expressions. So remember, this is a 2 even though it's not written, so it would be the 6th root of 125. Now, I could also try to simplify this a little more by trying to take out, we know 125 is the cube root of 5, right? That's one of those perfect ones. I'll show you guys anyway. So it's 5 and 25, 5 and 5. Why am I trying to simplify it a little more? To make sure it's easier to solve later. So we have the 6th root of 5 cubed. When I do that, I can write it as 5, 3 over 6. And that's going to simplify to 5.5. So you can leave it as 5.5 or the square root of 5. It is important to try to simplify the most you can. As you can see, even though if you plug it in the calculator, it will be the same. So I was saying, you want to have it as simple as possible. And the most simple one is when you have that root or radical as a prime number. In this case, the prime number being 5 became the square root of 5, or 5.5. If you left it as 6 root 125. We technically did simplify, but you didn't simplify all the way. Now, as we go on and we do more practice and we do the quiz review and the test review and all that, you guys will get used to it. But just something to keep in mind.